For as long as we have been human, we have looked up at the night sky. We have gazed at the tapestry of stars, the silent dance of the planets, and the milky river of our own galaxy. In that vast, silent darkness, we have always asked the big questions. Are we alone? Where did all this come from? What is our place in this immense, sprawling universe? These aren't just scientific questions, they are deeply human ones. They speak to our innate curiosity, our desire to understand the context of our own existence. Every pinprick of light holds a story, a history stretching back billions of years, and we have only just begun to learn how to read them. This quest for knowledge has driven us to build incredible tools. We have moved from simple naked eye observations to constructing ever more powerful telescopes. We built observatories on remote mountaintops, far from the glare of city lights, to get a clearer view. Yet, our planet's own atmosphere, the very air we breathe, acts as a shimmering veil, distorting and blurring the light from distant stars. It shields us, but it also hides the universe's deepest secrets from our view. To truly see the cosmos in all its glory, we had to take the audacious step of leaving our world behind and placing our eyes in the cold, clear vacuum of space itself. Humanity's journey into space has been one of relentless ambition. We sent probes to our neighbouring planets, landed robots on Mars, spacecraft past Jupiter, spacecraft past Saturn. But our greatest ambition has always been to look deeper, further back in time than ever before. We want to see the first stars flicker into existence. We want to witness the birth of galaxies. To do that, we needed a machine of unparalleled sensitivity. A time machine made of gold and mirrors, capable of capturing the faintest, most ancient light in the universe. A machine that could answer questions we haven't even thought to ask yet. And so, we built it. We built a successor to the legendary Hubble Space Telescope. A machine designed not just to look, but to see. To see in a different kind of light. Infrared that carries the secrets of the early universe, distant worlds, objects from other star systems. What is the James Webb Space Telescope? Well, in simple terms, it's the most powerful space observatory ever built. Imagine a telescope with a primary mirror over 6.5 meters across, composed of 18 hexagonal segments, each coated in a microscopically thin layer of pure gold. Gold is exceptionally good at reflecting infrared light, which is the light Webb is designed to see. It's a magnificent, shimmering honeycomb floating in the blackness of space, a million miles from Earth. It's a true marvel of engineering, a testament to what we can achieve when we work together. We call it the James Webb Space Telescope. Why infrared? Think of it like this. The universe is expanding. As it expands, the light from the most distant objects gets stretched out on its long journey to us. Visible light, the kind our eyes see, gets stretched into longer, redder wavelengths, eventually becoming infrared light. So, if you want to see the very first stars and galaxies that formed after the Big Bang, you need an infrared telescope. Webb is, in essence, a time machine. It's not looking at the universe as it is today, but as it was over 13.5 billion years ago, capturing the faint, ancient glow from the dawn of cosmic time. To see this incredibly faint infrared light, the telescope has to be kept extremely cold. Any warmth from the telescope itself would create its own infrared glow, blinding it to the faint signals from deep space. It would be like trying to spot a candle from a mile away while someone is shining a searchlight in your eyes. This is why Webb has a massive sun shield, the size of a tennis court. This 5-layer shield blocks the light and heat from the sun, the Earth, the Moon, allowing the telescope to cool down to a truly frigid minus 233 degrees Celsius. It is in this profound cold that Webb can achieve its extraordinary sensitivity. So, Webb is not just another telescope. It is a specialised instrument, exquisitely tuned for a specific purpose to uncover our cosmic origins. It can peer through the dense clouds of dust and gas when new stars and planetary systems are being born, something Hubble couldn't do. It is our sentinel in the dark, a golden eye patiently waiting to show us things we've only ever dreamed of seeing. For almost all of history, everything we studied in the sky belonged to our solar system. Comets, asteroids, planets, they were all our neighbours, born from the same protoplanetary disk that formed our sun some 4.6 billion years ago. They are part of our family, but in recent years, we've come to realise that we are not entirely alone. Our solar system is occasionally visited by wanderers, interstellar visit on unusual trajectories, objects ejected from their own star systems, travelling for millions, perhaps billions, of years across the vast emptiness of interstellar space. These interstellar objects are incredibly rare, precious messengers from across the galaxy. One such visitor, designated 3I/ATLAS, captured astronomers' imaginations worldwide. First spotted by the ATLAS survey system in Hawaii, it was quickly identified as something special. Its trajectory was all wrong. Not a neat elliptical orbit like a normal comet or asteroid. Instead, a hyperbolic path, moving too fast for the sun to capture. It was just passing through. It came from the direction of the star Vega. But its journey began long before that, in a distant star system we can only guess at. What made 3I/A Telos intriguing was its behaviour. Like a comet, as it neared our sun, it heated up and released gas and dust, forming a faint coma and tail. This process, outgassing, offers a priceless opportunity. By analysing the light passing through that gas, we can determine chemical composition. It's like doing a remote chemical analysis on a piece of another solar system. Because of this unique chance, the world's most powerful observatories turned to the visitor, and none were more powerful than the James Webb Space Telescope. The observation was scheduled for a precise window on the evening of September 7th, 2025. In the control room at the Space Telescope Science Institute in Baltimore, a quiet tension filled the air. This wasn't a routine observation of a distant galaxy, this was a time-sensitive intercept. 3I/8 Plus was already on its way back out of the solar system, moving faster and faster with each passing second. The team had one shot to get this right. The commands were sent across 1,000,000 miles of space, and the magnificent golden eye of the Webb telescope slowly pivoted, locking onto the faint, fleeting point of light that was their target. The data began to stream back to Earth, translated from photons of light into long strings of numbers that appeared on the scientists' screens. Webb's near-infrared spectrograph, or NEOSPEC, was the instrument of choice. It works like a prism, but an incredibly sophisticated one, splitting the faint light from the object's gassy coma into its constituent colours, or wavelengths. Each chemical element and molecule absorbs light at very specific wavelengths, creating a unique barcode-like pattern of dark lines in the spectrum. The team was looking for the familiar barcodes of water, methane, carbon monoxide. As the initial data was processed, the expected patterns began to appear. There was water, lots of it, confirming that this object was indeed comet-like. But then, as the computers refined the signal and filtered out the noise, something else emerged. It was a pattern in the data that didn't match any known natural chemical signature. It was a series of sharp, narrow-band spikes, repeating in a structured, almost mathematical sequence. It wasn't a chemical barcode. It looked different. A hushed silence fell over the room as more and more scientists gathered around the central monitor. They ran diagnostics, checked the instruments, and reran the data. But every check came back clean. The telescope was performing perfectly. The signal was real. When astronomers talk about a signal, they're not necessarily talking about a radio message that says, "Hello, Earth." The word has a much broader meaning. Imagine you're listening to the sound of a forest. You expect to hear the random rustling of leaves, the chirping of birds, the buzzing of insects. This is the natural background noise. Now imagine that amidst those sounds, you hear a perfectly rhythmic drum beat, boom boom cha, repeating over and over. That drum beat is a signal. It's an organised pattern that stands out from the randomness of the forest. The data from Webb was the astronomical equivalent of that drum beat. The telescope was analysing the infrared light from the gas cloud around 3I/8 Telos. The natural sound was the spectrum of light absorbed by various molecules like water, carbon dioxide, which creates a complex but well understood pattern. The drum beat was this new, unexpected series of sharp, narrow spikes in the spectrum. They were too regular, too structured to be easily explained by the chemistry of a simple frozen rock warming up. It was a pattern superimposed on top of the natural chemical signature, and it hinted at something more. So, the challenge for scientists was to figure out what could possibly create such a signal. And in astronomy, when you find a pattern that you cannot explain with known natural physics or chemistry, you have stumbled upon a major discovery. In the face of such a baffling discovery, the scientific community immediately went into overdrive, proposing and debating a range of possible explanations. The first and most critical rule in science is to exhaust all possible natural explanations before considering more extraordinary ones. So, the initial theories were grounded in physics and chemistry we already understand, albeit stretched to their limits. One of the leading natural theories involves the object's composition and rotation. Imagine a pocket of unusual crystalline material on the surface. As the object tumbles, that patch gets exposed to sunlight. The sun excites the crystal molecules, which emit infrared light at repeating frequencies as they cool. Another idea: interaction between outgassing and the solar wind. The result could be a natural maser in the coma. A maser produces a concentrated beam of electromagnetic radiation, like a laser. Natural masers exist in interstellar clouds, but they're usually broad and steady. Webb's sharp, repeating pulses would need a perfect storm of chemistry and physics. It is the idea that scientists are often reluctant to discuss openly for fear of ridicule. But in the quiet corridors of research institutions and in hushed tones over late-night video calls, the question was inevitably raised. What if 3I/8 Telos isn't just a piece of rock and ice? What if the signal is artificial? The implications are staggering, almost too vast to comprehend. It would mean the rhythmic pulse detected by the Webb telescope is not a quirk of exotic chemistry but a deliberate broadcast, a beacon, a signpost, or perhaps just the faint hum of an engine from a machine that has been travelling through the dark for millennia. We call this the technosignature hypothesis. A technosignature is any measurable evidence of technology from another civilization. Could 3IA Tellus be an interstellar probe like Voyager but vastly older and more advanced? The pulses could be the infrared signature of a propulsion system, a power source, a piece of scientific equipment operating on board a dormant or automated craft. The thought is thrilling and deeply chilling. The notion that we might have been visited by extraterrestrial technology is a paradigm shift. It would mean we are not alone, that another civilization reached interstellar capability. It would transform Are We Alone into Who Are They? Where did they come from? It's a ghost in the machine, a whisper from the stars. The discovery of the signal from 3IA Tellus, whether natural or artificial, has irrevocably changed our perspective. We are left standing at a crossroads faced with a mystery that strikes at the very heart of our place in the cosmos. Regardless of the final explanation, the universe has revealed that it is more complex and surprising than we ever knew. If the signal is a new, natural phenomenon, then we have discovered a new chapter in physics and chemistry, a new way that matter and energy can interact in the universe. It would open up new avenues of research for decades to come. But if it is a technosignature, then humanity's future is forever altered. The confirmation of intelligent life beyond Earth would be a unifying, and perhaps terrifying, moment for our species. It would end our cosmic solitude. The discovery would galvanise a global effort to understand the signal and its source. The immediate next step for scientists is clear more data is needed. Urgently. Unfortunately, 3IA Tellus is speeding away, growing fainter by the day. Every major telescope on Earth and in space will be marshalled to observe it, to try and capture more of this enigmatic signal before it fades forever into the interstellar darkness. They will search for similar signals from other interstellar objects, turning this one-off anomaly into a potential pattern. The search for extraterrestrial intelligence will no longer be confined to just listening for radio waves. It will now involve looking for these physical infrared whispers. Ultimately, the signal from 3IA Tellus is more than just data on a screen. It's a question mark hung in the heavens. It represents the very essence of science and exploration, the pursuit of the unknown. We live in a cosmos filled with wonders we are only just beginning to perceive. And now, our greatest adventure is to find out what or who is making it. The journey has just begun.